You can see here that the NVIDIA object-oriented agent consumed 33.5% less tokens compared to a simple native tool calling loop or an agent. But I want your attention here, right? You see, after this particular docstring, there is just an ellipsis and there is absolutely no code whatsoever in this particular method. And that's the beauty of the NOOA agent is that everyone, the goal of this particular demo is that we'll be comparing a regular agent written using loops and NVIDIA's object-oriented agent. Or the task is basically we check if all the items here in this particular queue that you're seeing fit my budget of $15. That's what I want to check. So what we intend to do is get each item from the paginated queue, collect the item names and prices, compute the total cost, and decide if it fits the budget. Very simple. Now let's see what happens. Now let's run the agent. Now let's actually run both the agents together. So the first agent is a simple loop agent, which is iteratively checking the price, the item and the price of, and doing the computation. So as you can see, it's checking the price of elderberry, which is $6, and checking the price of figs, which is $1.8, and doing the computation. It's a very simple math. It just needs to basically take all the items and then add all the price of all the items. Now we finished with that. We have moved on to the next agent, which is NOOA, NVIDIA's object-oriented agent, and we have finished the task. I want your attention on this bit first, which is basically the result. As you can see, the total cost by both the agents was absolutely correct. It's 22.6, and it doesn't fit the budget. It's saying false for both fits underscore budget, right? And we know that there are 8 items. Perfect. But here is the part that I want your focus on. You see, our simple tool calling loop, which is probably most of the frameworks today, which work on the items iteratively. You can also look at parallel processing also. But the point here is that even if you're doing, no matter what you're doing, sequential calls or parallel calls, you still are making n number of calls. So the naive JSON tool calling loop, a simple agent that we built, had total token count of 10,154. That is the input tokens. And completion was 669. So the total was 10,823 for 10 LLM calls. The NOOA agent, which is basically NVIDIA's object-oriented agent, took just the input prompt was just 6,910 tokens, and the completion was just 284 tokens. So the total was 7,194 tokens, and it just made 2 calls. You can see here that the NVIDIA object-oriented agent consumed 33.5% less tokens compared to a simple native tool calling loop or an agent with a loop. Obviously, what you saw is my own demo that a custom to different agents that I've written. You can choose to ignore the numbers. But what's interesting is NVIDIA recently published this particular paper, and in their own official benchmark, and if I can go to their blog, you can see in the SWE-bench or the SWE-bench, the NOOA agent has solved more problems while using roughly half the tokens. Same models, no prompt compression, no magic, just a completely different way of building AI agents. Let's understand how. In this video, we'll cover what is NOOA, that is NVIDIA's object-oriented agent, what is the problem it solves, how it is different from typical agent from frameworks that we've been used to seeing. We'll also do a couple of live demos. One is obviously the token savings demo and some core features and their demos as well. And we'll also see what is the caveat for this particular framework, and should you be actually using this. All right, let's get started. The problem every agent framework has. If you have ever built an AI agent, you probably notice something frustrating. You write a function, then you write a JSON schema describing that function. Then you explain that function again in a prompt. Then you wire it into a workflow. One tool, 4 different places. Here's the strange part. Python already solved this problem years ago. It already has functions. It already has classes. It already has type hints. It already has objects. So NVIDIA asked a simple question. Why invent an entirely new language for agents? The question became NOOA, NVIDIA's object-oriented agents. So what exactly is NOOA? The biggest idea in this paper is surprisingly simple. Imagine your AI agent is nothing more than a normal Python class. That's it. The method becomes tools, the variable becomes memory, the docstring becomes instructions. Your type hints become rules that runtime can enforce. Instead of learning a completely new framework, you just keep writing Python. That's the philosophy behind NOOA. All right, let's actually implement a simple example given in this particular white paper. So if you scroll down a bit, you'll see that they've given a very simple implementation of the agent. We'll try and implement this and run this actually and see how this works. But before that, uh, it's very easy to essentially install uh, the NOOA package. You could either use UV or run the pip command to essentially install NOOA, that is pip install NOOA. And once you're done with that, let's implement this. So I've actually done that already, and we'll see what or how we implement this particular agent. So we'll be using the NOOA package and the agent class from the NOOA package. We'll also be using the getLLM client method to essentially give us the LLM object. Now, if you look at the core of the agent, which is basically the feedback agent, it is inheriting the agent class that we just saw. And also we are passing the LLM object as the argument that we just created here. For this particular example, I'll be using Claude's or Anthropic's Claude Haiku model, Claude Haiku 4.5, and we'll see what are the tools or methods that are available. So this particular agent uses this method, which is analyze feedback, and the prompts or basically the skill of this particular agent is called out in the docstring. So we are saying that you're an agent specializing in analyzing customer feedback here. And for the tool or the method that is available as part of the agent, analyze customer feedback for sentiment and key topics in one sentence. But I want your attention here, right? You see, after this particular docstring, there is just an ellipsis and there is absolutely no code whatsoever in this particular method. And that's the beauty of the NOOA agent, is that it essentially writes the code for you given this ellipsis. So this ellipsis is telling the framework that from here it needs to basically implement the relevant code and execute the task. So let's see actually how this works. So I have a simple method, a main method to essentially invoke or run the agent. So I am instantiating an instance of this particular feedback agent. I have the agent object ready, and I'm calling the analyze feedback method. The agent's goal is to essentially, given a product review, it analyzes the feedback or a review of the product and gives you the sentiment. That's it. It's essentially a sentiment analysis agent, right? So I have this particular string here, a product review, great product, but shipping was low. And let's see what happens. I'm going to run this now. And you will see in a bit, we should get the output of the agent. All right, so we have the response from the agent. The feedback expresses mixed sentiment with satisfaction about the product quality, but dissatisfaction regarding slow shipping delivery. Yeah, makes sense, correct? Now, let us tweak the agent bit, and we'll give it an extra instruction, and we'll say response structure, and we'll say start with analysis, sentiment, and key topics. Okay, and let's see if the agent, just by looking at the docstring, is able to generate a structure. I'm not giving it any JSON or anything, but I'm expecting that it returns this particular structure. Let's see if it is actually able to do that. All right, so we have that. The analysis, the customer is satisfied, and there is another key, which is sentiment, and another key, which is key topics. So it's that sentiment is mixed, and the key topics is product quality and shipping speed. All right, I mean, you can imagine that you can give it any kind of structure that you want, but you could still say that, okay, no, this is simple LLM call, and it's probably not a very complex use case. But I want to show you a very complex use case. When I say complex use case, we'll be taking a very simple example, but the use case is going to be relatively complex from what we are seeing. This is the agent simple agent demo that we have in the white paper. But what I've done is I've also implemented a weather agent, which is relatively complex. And let me actually walk you through what the agent does. Again, we are importing a few classes here, which is essentially a tool call event and Python output. The idea here is that we are able to iterate on what is the code that the agent is generating, and we can print that on the screen. Nothing else. You don't actually need this. Maybe if you're using this, you only need the getLLM client method and the agent class. All right. What I have done is I have implemented this weather agent. And this weather agent essentially given the location, it essentially returns the weather information for that given location. All right. There are two tools or two methods here. One is get current time, because the goal is that I'm also able to generate the current time of a given location. As you know, the LLMs will not do that, and they don't have access to current information. So I'm actually expecting that the agent is able to generate a code and returns that particular response, which is basically the current time. And the key tool here is basically get weather, and I'm passing this particular argument, which is the location. And this is the this is the prompt, and I want your attention on a couple of things here. One, I am asking it to essentially within the prompt here in the get weather, I'm asking it to execute get current time so that it has the current time of the given location. And I'm also asking it to read open map weather API key, which I have used in my environment file here, and to read this from the environment as basically as an environment variable. And all of this will happen at runtime, and it generates a code, right? I have not explicitly asked it to basically use the open weather map API endpoint. It has that already as part of its training data, so I'm not doing that. I've tested this already. I'm just letting you know. And what I want is that I want it to basically return a response in a human readable format. Uh, you see, there are a few things here, right? You can ignore this piece. We are just printing what the events are, what the code that was generated. But I want you to pay attention to this part here. I have absolutely written no code for it to basically, make a REST API call, that is use the API key and use the URL, that is open weather map URL, and then call that particular API and then return a response. I have not done any of that. I've written zero code either for this method or for this method. I expect the agent to generate that particular code and execute that at runtime. Okay, so let's actually run this particular agent once and see the response, and then we'll probably debug this line by line and understand what's happening. Let us run this first. So I'm going to clear out what we had earlier. I've just started the agent, and let's see what happens. All right, so we have the response, and I want to show you the response from the top. There was a lot that this particular agent did, but let's actually look at each and every output, essentially the response that we got from the agent. The final response from the agent is just this, right? Let me be very clear. This is the response. You'll obviously not see so much response. We have printed essentially like logs of whatever the agent is doing, or all the events the agent essentially executed internally. But the final response that we got from the agent is this. Uh, in fact, let me actually show you what was my prompt. I think I should have called it out earlier. My what I've done here in the main method is that I have instantiated the weather agent, and I am essentially executing the get weather method, and the I want the weather for the location Bengaluru, and this is the response that we got from the agent. I'm printing a lot of output here, but let's actually see what happened. So this is the code uh, the the agent generated, right? So first it did was it basically is saying inspecting inputs for get weather, so it knows that it needs to execute this one, and it has essentially generated all of this for us. So this is the code that it has generated to execute get weather, and as you can see, uh, you know it uh, it is importing some libraries, and it has written this get weather method, and the get weather method has current time, and you see that it is also invoking this method, which is await self dot get current time, and we'll get to that in a bit. The get current time method is something that it still needs to implement, but we'll see how it has done that. So if you see, the get weather IMPL method is basically a method that it has created to run in the REPL, and it was also able to figure out what is the OpenWeather API and how it needs to pass the parameters, which is basically the location that I sent, and also utilize the API key of OpenWeather API key, which I have actually written in my .env, and it was able to essentially generate that. So this is the code it has written. It's a very simple REST API call that is using it, making using the URL lib package. And as you can see, it invoked this particular method, and it is printed the data. We'll see what that looks like. There is one more implementation as well, right? So it has also basically written this method. If the current hour is you know less than or equal to 5, or greater than or equal to 5 and less than 12, then this is what the suggestion should be, right? I have not asked it to do it, but I think it is written that on its own. And this is the format that this particular method returns, whether it's this, temperature is this, right? There is another part, right, which is basically the get time method. If you look at the get time method, basically it has implemented this code for the get time method, which is, or written this code for the get time method, which is def get time zone. It has basically created time zone map, and depending on the input that it was given, it has written that particular response. As you can see, it used the pytz or Python time zone library, and it was able to get the current time given the location. Essentially, it was able to figure out what the time zone is for the given location and generate the code. So all of that, it basically wrote the code for us, executed that particular code. As you can see, it was able to return the response. This is the response that we get from the OpenWeather API. And once it was able to consume that particular response, it was able to return this final, code for us. As you can see uh, in the code, if I can show you this, it is also parsing the response from the API. So if I get to this part, as you can see here, uh, let me go to this section. Temperature is this, weather data of main of temp, description, what that weather particular description is. All of that extraction also, it has basically figured out what the response is, and it is written. So if you get to this part here, the final response is weather in Bengaluru is 23.94 degrees centigrade. The current time is 9:35. We ran that at 9:35. It's already been 4 minutes since we ran that. And locals are having breakfast and coffee, obviously, because it's 9:35 in the morning. So you see how powerful this particular setup is, where the agent is able to generate the code, execute the code given the information. It looked at, let me go back to the code. It looked at the docstring as prompt. It was able to essentially understand that these are the methods that it needs to write the code for. It wrote the code, executed the code for us, and it essentially made tool calls in the language of the agents, and then returned the response. All of this was done without us having to write explicit code for get current time and get weather. I thought that is very, very powerful. And in fact, if you go back to the the token generation demo that we did in the beginning, that is exactly what is happening here as well, right? So if I show you this particular agent, which is basically the agent that we had to, essentially check if, let me actually show you that. This particular region, right? So if you wanted to see that if the list of items are, if they fit in my budget or not, which is with the budget of $15, the code for that looks something like this. And I'll get to the agent bit immediately. you can see that I have a queue agent, and the queue agent has, again, we are instantiating or basically inheriting the agent class, and we are passing the LLM object here, and the model is something that we are, capturing, as input. You see that it has two methods: get next time and get next item and total queue. Uh, I have not written the ellipsis here, so it returns the get next item. It's just simple. But what this total queue does is this is where it expects to the code to be written, and that's exactly what has happened, right? It wrote the code for us. And when I show you, in fact, let me actually run this again, right? So you see the output again. I'm not, I don't have the detailed logs printed for this one, but we'll see that again. All right, so we are obviously doing a comparison. So, we first finish this. Now the NOOA agent is in action, and we will have the final response now. As you can see, NOVA consumed 32% less tokens to execute the same task, where, a loop, if you would use loop, either serial or parallel loop, to execute the same, uh, queue-based actions that we saw, right? Now, where do the token savings come from? This is the question I kept asking while reading the paper. How does NVIDIA cut token usage almost in half? In my case, obviously, when I was running the test, as you can see, I was getting, a 30%, but, the white paper says that they were able to get, the NVIDIA team was able to get, able to get the token usage almost in half. The answer, and according to the white paper, is not and it's not a trick. It's actually three smaller design decisions working together. Let's actually look at each one of them. The first one is code becomes the action. And I want to, go to the PPT now. Let's start with how most agent frameworks work, right? So the model wants to call a tool, and the the tool essentially generates some JSON. The framework parses that particular JSON. It calls the function. Now let's actually start with how most of the agents work, right? So the model wants to call a tool. So it generates a JSON. The framework parses the particular JSON. It calls the function, converts that result back into text, and then sends all of that back to the model. The entire loop repeats every single tool call. And that's something that we saw in the previous example, right? So if we had, I think, close to 8 items, and we had to repeat the process of, calling an LLM for each and every item. That is, we had to make 8 different calls. Even if it were parallel, it would still be 8 different calls, right? NOOA, that is NVIDIA's object-oriented agent, works differently. So what in this case the agent does, it simply uses a model to write Python, and here you get no JSON, you have no parsing, you have no translating. The model writes the code exactly like a developer would, right? And we've seen that example previously, right, where we saw the model generate complex code just by reading instructions, call APIs, uh, call different tools, generate long methods. All of that was written by the model, but the framework enabled that, right? So instead of doing all of this manual work of parsing, I would say manual work, the overhead of, taking in a lot of token in terms of text, it would basically use or generate the code and execute the code itself. I think that's a big takeaway. And that's one of the techniques how the token saving happens. We'll go to the next one now, which is pass by reference. And I would say this is my favorite part of the paper. Uh, Imagine, you ask an any agent, right, to analyze a spreadsheet. What most of the frameworks do, like LangChain or any framework would do, is basically they would take that Excel file, convert that Excel file into a string object, basically serialize that. You then turn that as context to the prompt, and essentially you hope that the context window is big enough to handle that prompt and execute that. NOAA does obviously things a little differently. It gives the model, basically it takes the entire object, Excel object, and gives it to the model. The prompt only contains a tiny preview, but the actual job is done by the code that is generated by Python, right? Or the code that is generated by the model. I have a simple example that I'd like to show you guys. This is the pass by reference example. First, look at the structure of what we have, right? So I have three classes here. One is artwork, the other is stock holding, and the other is jewelry. You can think of these as three different operations that I have for my agent, and these are regular classes. You see that I'm not inheriting, a different class here. This is not an implementation of any other class. It has the init method and it has a method. Each of these classes have their own method. The artwork has get appraisal, and the stock holding class has get total value, and the jewelry class has get compute value. There is some computation that is happening. I'm creating an object which is basically a key value pair of, let's call it a SKU, or a product ID or an item ID, and the relevant object that we have instantiated. So for example, art001 means the artwork, the value is basically an instance of the artwork object, which has all the arguments that are passed to it, which is in this case, in the artwork case, it is the title, the artist, and the appraised value, right? Same goes for stock holding. We are essentially passing the shares and the number of shares and the price per share. And for jewelry, it is basically carats and rate per carat. So let's actually see how the agent is written now. So we know that we've written this particular part, which is basically the get item part, where the get item is essentially a tool, and the tool essentially returns one item from, given the item ID, it returns the that particular item's object. This is how the agent looks like. There is a warehouse appraiser agent. We are using the agent class that we saw previously to essentially the warehouse appraiser inherits the agent class. We're also passing the LLM object that we saw previously. And as you can see, there is no other code written here. It has only one method, which is basically an appraise item and the ellipsis as an instruction for the agent to write the rest of the code. So the prompt is agent that appraises items without knowing their types ahead of time. So we know that the agent doesn't know what kind of type it is. It doesn't know what value it needs to bring, but it'll basically figure that out at runtime when it executes the code. So you see, uh, get the monetary value of an item. So I'm saying that get the monetary value of an item, and each of these objects have a different implementation of what that value is. So in the case of artwork, it is currency, that is whatever the value is. Sorry, it is the value here, self underscore appraised value. It is in the case of stock holding, it is basically a product of self dot shares and self dot price per share, which is basically something that I'm saying. So if it is 100 shares and the price is 2, then I should get the value as 200, which is basically a product of shares and price per share, right? Similarly, for jewelry, the output is completely different. As you can see, the method that we are executing is in complete compute value, and we are again returning the product of carats and the basically number of carats and rate per carat, right? So let's actually execute this. You can ignore this particular code, which is basically, we are just trying to print the event so that we know what code was generated. But the important bit is that when I run this main method, it is iterating over 3 SKU values that we saw, or 3 items that we saw. The get item will be used to essentially retrieve what that item is, basically get the object of the item relevant here. So if you see underscore warehouse, there are three items here: art001, stk001, jwl001, and each of these returns an instance of these classes, which is obviously completely independent of each other. And we are not passing that as instruction anywhere. we're just doing this at runtime, and let's see if that actually works. So I'm going to execute this particular or run this particular agent now and see what happens. So it is obviously iterating a couple of times. It's making multiple LLM calls, but it got the appraised value correctly, which is 15,000. And okay, I think it finished everything, but let's look at this. So we know that the appraised value for art001 was 15,000. It precisely got what that value is. Remember, the task here is get the monetary value of an item. So for every item, I'm trying to get the monetary value. Uh, and I'm nowhere saying in the prompt or in the doc string what that value is, how it can basically read the value from this particular thing. It is figuring it out by reading the objects on its own. So I will show you the first one, which is basically the art001. And we know that art001, we passed the appraised value as 15,000, and that's exactly what we got, right? Which is basically the value of an item. The next one is stock holding, and the values that we had there was 100 shares and price per share, and we know that the value is basically the product of 100 into 875.5, and that's the exact value that we have gone. It has written the code and executed that. Basically, it's executed that particular method, and we've gotten this particular response. Same with this one, which is basically JWL001, which is basically the jewelry object. And it had 2.5 carats, and rate per carat is 8,000, and the final response that we are getting is $20,000. All of this happened, and as you can see the code here, all of this happened without the without us explicitly passing what those objects are as prompt. That's what we are used to doing, right? But the agent was able to perform. Basically, it was able to understand the object and then execute the code and utilize the object's references, that it was able to reference the right properties of the object and return the response for us. So another very important concept on why this particular this particular agent does so much less consumption of tokens is because you don't have to serialize all of these properties and pass that as context to the LLM or the agent. It does on its own. It can take in objects like this and then is still able to figure out how to make the object or utilize the object properties to essentially get the relevant value out of that. That's what we saw, right? All right, let's move on to the next section, which is basically, I'll go back to the PPT here. So we looked at code as action and code passed by reference as the two core features on how it is able to reduce the token. There is another one, which is basically typed IO, and basically you can enforce certain guardrails in the code without having to explicitly say that, and the agent is able to figure that out and then do this or give you the relevant output by executing that particular validation. I think when I run the code, you should be able to understand that. Let's have a look at that particular code. You see, this is the validated method. Let me actually start from the beginning again. So this is the agent. I have the feedback analysis class. It is basically a pydantic class, as you can see. And I have, it has a couple of properties: sentiment, topics, urgency, summary, and there are type hints everywhere. You can also see that we have implemented a field validator for the summary, which is basically the summary should not be more than 3 words. That's what we want, right? If it is more than 3 words, an error should be raised essentially. And let's look at what agent we have. The agent is basically the same agent that we saw previously, which is basically the sentiment analyzer agent. And I'm going to run this now, and we'll see how this works. The agent is running. And the first time, I think it got more more words. So it is basically trying again. Second time also, I think it got more words. It's trying again. I think in the third attempt, it was able to complete it. So as you can see, I'll quickly walk you through what the code is. So we've instantiated the feedback agent. We are looking at the analyze feedback method, which is basically to get us the sentiment analysis. And the feedback is broken feature needs immediate fix. And as you can see, when we were iterating over the result, we saw that it used the validator to, uh, you know, when even when the, it just didn't return a response randomly, right? It was able to, without us explicitly mentioning that there is a validator there, it was able to understand that there is, there is some validation that it needs to execute and, or at least need to see or validate. It saw that on every attempt, it was not getting less than 3 words. And at the third attempt, it was able to get the 3 word, and that's what it yielded. And the confidence score, though high in all the iterations, the number of words were obviously a little higher. That's why you see that it was able to fix it. So the idea here is, and let me go back. The idea here is that without us having to explicitly write those guardrails, as a sequence of steps or as part of the workflow, the agent was, because we mentioned that as the output requires this validation, which is basically the feedback analysis. The output is of type feedback analysis. It was able to validate that and iterate on the response because it was getting an error. It realized that it can basically, uh, generate a proper and a relevant response. And finally, after this particular condition was met, uh, or not met, it was able to return that particular response. So three different types of core features of this particular agent that makes it so much powerful, which is code as action, pass by reference, and typed IO enforced, right? All right. Uh, Before we conclude, something that I'd like to call out is that this particular model or this particular concept is still in research stage, and you need to use this very carefully. You don't want the model to generate arbitrary code and run that in your systems. You want to ensure that your system is sandboxed. You're running this either in a container or using NVIDIA's open shell project, but never on your primary file system. I've been running that, but I've been giving it very simple examples. But the idea is that you don't do this. This is still a research project. I'm sure there are going to be a better versions of production version of this, where you could isolate the code execution into an independent container or isolated container and then execute the code there. But the idea here is that you can see that the efficiency in terms of token is very, very high, and given the right uh, robust settings to execute the code, uh, I think this can be a game-changing framework to work with. I hope this was useful for you guys. I hope you guys enjoyed this particular video. If you haven't subscribed to this channel, please subscribe. And we will keep exploring new agents, and we'll also continue on the harness engineering series that we were working on. That's all I had for today. Until next time,